right, time for another DraftPhysics.com, debatephysics.com also. But again, it's hard to find any physicists interested or willing to participate in any conversation, about the fact that there could be, some I don't know, wrong guesstimates in what the established physics has established as the truth, and that some of this stuff needs revisiting or deserves some more attention than has been given. These fundamental, elemental assumptions of physics, declarations of physics is what they really are. So anyway, physics says it does take 100 times the energy to spin a motor 10 times as fast. That's a clear obligation of their axioms of reality, and it really doesn't make any sense. I don't think anybody has any personal experience where that is the requirement, and yet they just march forward and continue to tell us the story. So I found another guy here. He physics made easy, and he does tutor. So for $145 or so, he'll spend a couple of hours trying to explain physics to you personally. And so we'll see if he's willing to do that publicly, to explain to me why I'm an idiot and I'm wrong and I don't see what they see. Even though I've spent 10 years now devoted essentially to the subject, searching for what they see, and I can't see it. And I don't think, frankly, the frank truth is, I don't think physics is being honest to the true history, and I think it's making some assertions that are just boldly wrong. Now, we could disagree about a lot of the foundations of physics, and we do. Okay, I mean, I don't think you have the atom right. I don't think you have gravity right. I don't think you have anything, frankly, right, in the big picture. But let's devote ourselves just to this one aspect of physics where they've accepted a duality, where we have these two definitions of energy, momentum and some sort of thing called kinetic energy. M1/2 mv squared. You could sort of forget about the 1/2. It's a constant, so who cares? In a lot of ways, it's always going to do the same damage to the proportions. So it's really just this idea of why you would square a velocity and what merit it has as an idea, where anywhere it has ever answered a question that mattered. Do lunar modules use 1/2 mv squared to calculate the thrust that's going to land them on the moon? It's questions like that need to be answered definitively. A physicist should know one way or the other whether they were calculating the thrust based on kinetic energy or calculating the thrust based on momentum. And these are questions that should be answerable. And so I'll bring up a couple of points. This guy's name is Edouard Andre Rennie. I think that's something like that. Anyway, he's a material scientist, so he has a doctorate in solid-state chemistry. So it's close to physics, we would imagine. So I'm just going to read a little bit of his profile that he put up on YouTube, and I'm not critiquing, I'm just pointing out that I if the objective is the truth, people who are, teaching it should be willing to defend it occasionally. I mean, it doesn't happen very often that they're requested to defend what they're saying. Students don't usually have the wherewithal to challenge, but they should be willing to answer the challenge. So anyway, high school physics courses provide the foundation of everything we know about physics. And my argument is that foundation is overtly dishonest in the sense that Newton didn't say 9.8 meters per second squared. He said 9.8 meters per 1 second. It's a ratio. It's how much you get per second, not per seconds, and certainly not per seconds squared. And he clearly stated that momentum and force are proportional. That is, a force is really just momentum. It gives things momentum. It takes momentum away from things in equal proportions. Twice the force, twice the speed. 3 times the force, 3 times the speed. Those are Newton's exact words, essentially. Very close to a completely accurate paraphrase, let's just say. All right, so it says, do you want to learn what physics actually is? So this is your statement. I mean, and I can't. There's no way to, in some super. I can't. It's like super elastic. I can't be super polite and say, I don't think. Okay, what you're saying is actual. I don't think it's actual physics. I think it's pretty much just contrived, and I'm going to call it a fable. I don't think it's really based on evidence, and I don't think it's based on good reasoning. That you violate basic laws of logic in the sense that there's overt contradictions in your wave particle and in your duality of what energy is. Okay, why it's so awesome? That kind of stuff is just so, clickbait. I don't know what to call. Come on. It's acquisition of understanding is usually a bit tedious and annoying, not awesome. But anyway. So join me in a journey to understand the amazing universe we live in. I'd say, it's actually a terrifying universe, and everything will be, annihilated in some horrible way, which is, hardly a great thing. But whatever. It's, so he says, physics made easy prevents crash course videos exploring the main areas of physics via lessons and high school exam preparation. Now, yes, that's, if you want to pass your catechism, you could probably use some tutoring to pass the catechism. Does the catechism have anything to do with reality? I don't think so. You can also find some what is videos, and this is the argument. I don't think you're answering those questions exactly accurately. And that's saying it as nicely as I can say it. I don't think it's exactly accurate, but the truth is, if I was going to be honest, I'd say bullshit, okay? It's just bullshit. These provide a simple and clear explanation. So I would say, again, it's a very tailored description that avoids accepting the huge, gigantic, monstrous paradoxes you create. So the fact is, the theory is completely paradoxical and it doesn't work. All of Newton's laws were describing a world where there is absolute space. That is, the space is actually still. Okay, a piece of space doesn't move anywhere, and everything moves relative to that absolute. That's the world Newton lived in, and all the energy is quantity of motion. It's just how much mass and velocity, and that's all the energy that was in the universe. There wasn't any kinetic energy. So the laws are clearly not written to describe anything called kinetic energy, and simple things like the gun and the bullet violate those laws because they create completely imbalanced outcomes. 2,000 joules going one way, 2 joules going the other way can hardly be called an equal and opposite reaction. I don't think fairly or reasonably. So I don't think that's reasonable. Frankly, there's no way to say kinetic energy is in any way consistent with Newton's laws. The second law is where he says overtly 1 unit of force, 1 unit of velocity, 2 units of force, 2 units of velocity. He clearly states 2 units of momentum, frankly. That's his statement. And okay, there's no 4 units of force for 2 units of velocity. All right, so I'll start by just making my argument. We'll play a clip from one of his videos. If he'd like, I'll play all of his videos all the way through. But I don't know if he'd like me to do that. But I can do that and point out the places where I say there's an error being made. So what I'm going to do is play this extended version of his video on momentum. And if need be, I'll play the one on kinetic energy, but there's frankly, not much material in there. So anyway, yeah. So first, let's just do a simple thought experiment, and just to illustrate the point that I think I can describe more than one of these circumstances that shows the paradox and shows that the physics just isn't right at minimum. It's not complete, as Einstein would say. It's not a complete theory of our reality. All right. So leave us continue. All right. So I have attempted to use this example many times about rolling something in friction. And so you have the same object, and all you're going to do is give one of them twice the velocity. So this one has twice the velocity as this one. Well, that's unfortunately not very dark. Always something, really. Probably could make it a lot bigger, but I wanted to save room. So what I'm really going to do is do this same experiment of rolling something. So the argument is this is all dictated by Galileo. Galileo basically said, you can roll things down a ramp, and frankly, you can have a 0-degree ramp, and you get the same results. This is what friction does. So it was really a theory about how you take something and its energy away. And the argument is this object will have this linear velocity, and its linear velocity is going to be consumed by the ground. In simple truth, the energy that's in this object rolling is going to be eventually in this ground, and then this object will stop rolling. So it'll cease to roll because friction took its energy. The energy this thing had is now in the ground as a form of heat, you could argue, vibrations of different kinds. And the simple argument is that when the 2x object is rolling, it's rolling right along, and then when it's going 1v, which is here, 3/4 of the way down the track, this is where it's going 1 velocity. So it starts with 2, it goes 1 velocity at this point. I don't think a physicist will disagree with that. And the simple truth is that it did just as much work here as it did here. This is the same unit, 1 unit of time. This is 1 unit of time. This is 1 unit of time, of course. And this experiment is essentially this. So this whole adventure here is exactly what happens here. These two things are exactly alike. And the ground absorbs the same energy in these two circumstances. 1v, 1v, you get a certain amount of distance, 1/4 of the distance, and 1/4 of the distance, right, and 3/4 of the distance are here. And so it's just, I really have to get another pen. Unfortunate. All right, didn't test this one, but we'll hope. Okay, so this is 3/4, all right, of the voyage, and this is 1/4 of the voyage. So it's just like falling in gravity. All right, the same event happens. I drop something 1 unit of distance, dropping it 4 units of distance. After 4 units, it only has twice the velocity because it only collected 2 units of gravity, 2 units of time, 1 second, and then the second. This first unit of time, second unit of time, 3 units of distance in the second unit, but only 2 units of the force, the 9.8. Only 2 9.8s for this whole voyage. And that is essentially just duplicated in the friction. So here you're not taking the energy until you hit the ground, and here you're taking the energy. Okay, so it's the simple argument is if you took all the energy that goes over this entire area here, it's only twice the energy. It is not 4 times the energy. So 4 times the distance is not 4 times the energy. It's only twice the energy. That's all you took. That's all the heat you created. If you measure the watts of movement in this ground, you'll find that there's only twice as many watts in this 4 times the distance. The ground absorbed much less here because of the speed. Now my simple conversion of this simple experiment was to say, say we made a sheet of ice. So I'm asking you as a teacher of physics, I make a sheet of ice and I have the ice just right. So something will fall through the ice, okay, if it stands still on it. So I have a weight that falls through the ice, all right, if it's standing. And the simple argument would be is that I could slide it across the ice, okay, at a velocity, and that no matter what its velocity is, it's got enough velocity that it doesn't fall through the ice, and that it will only fall through the ice when it finally stops, because then it's putting its full pressure on the ice. And at every other location, it's putting something less than. It's the pressure starts increasing as it slows down. It's getting heavier and heavier, essentially. Its measurable weight, okay, increases as it slows down. So if I did just make scales, if I just made a bunch of scales and put them as the surface, so we have a bunch of scales and they're just going to measure, okay, how much friction, how much weight is being placed on the road surface. I think a physicist would agree that as the object, I throw it, as it slows down, it weighs more and more and more. So there's less friction here than there is here, than there is here, than there is here, than there is here. It just gets heavier and heavier, and it causes more contact with the ground, and it loses more energy. So the simple truth is, yes, you lose more energy here. You lose the same amount here in this little space that you lost in this entire 3 times the space. That's the simple argument. And I don't think anything I stated here could be demonstrated to be incorrect. And in my opinion, it proves there's no kinetic energy because clearly all there is momentum. Twice the velocity is twice the force. It's not 4 times the force. It doesn't take 4 times the energy to make something go twice as fast, and when something goes twice as fast, it doesn't have 4 times the energy to give. It only has twice the energy to give. When you suck all of its energy out and convert it into just heat, you only have twice the heat here. Twice the heat that you'll have here. Not 4 times the heat. Proving there is no mv squared. Now I could give you the history, right? We could talk about the history where Leibniz invented this. Newton opposed it for 40 years. Newton had his surrogates make these kind of arguments that levers won't work, lots of things won't work if you believe this. Okay, it's not the truth. The truth is that quantity of motion, momentum, is the only energy there is in the universe. And the force, of course. The force is a quantity of motion. Okay. The force is a stream. I mean, I actually wrote this down here just because his energy video has a statement. So I wrote down, streams give their motion to objects, their momentum, their MO. And that's what they do. So any force that's giving something momentum, you're actually taking something from the force. So if I throw boats into a stream, I do make the stream flow slower. I slow down the water because now the water has pushed a boat. Its energy has been given to the boat. So the more boats I throw in the stream, the slower the stream moves. I'd say that's another absolute fact. All right, so let's play his version, and then we'll do one more little. We'll do a a redefinition of his definition of his experiment. We'll just change it a little tiniest of bits, and by changing it a little tiny bit, you will see how yes, it doesn't make consistent logical sense. That it creates what can only be called a paradox. It just can't really be the truth. That should work. And so leave us begin.
Now, in order to demonstrate how to use conservation of momentum to solve problems in physics and find stuff, let me present to you Bob and Alice. Alice loves to go skating. So now she's skating, right? So put some skates here. I hope you admire my drawing qualities.
I love drawings, so that's very good. I love illustrating physics, okay, with a dynamic model. A lot better than I like a bunch of silly Latin symbols twisted upside down and inverted and switched with each other and all that mathematical crap.
And I'm going to put Bob here. He's skating too, because Alice invited him.
All right, so he's talking about skating, which is cool because, I've been using this analogy of thin ice, and the fact is you go across thin ice with a velocity, you're less likely to fall through the ice, and the simple reason is because you're giving less pressure. You're giving away less of your energy to the ice. So the way we're going to change this just subtly. All right. Sorry, I have to do this switching. I think it just keep it consistent. All right. So he's using two objects, and he's going to give them quantities of motion. All right. And so I'll do the same thing here, except I'm going to show that I'm not going to give the object with more momentum more kinetic energy. What I'm going to do is give the object with more momentum less kinetic energy. And then you'll see the paradox. So if you do the example one way, everything seems to be okay. But if you do the example just changing one factor, everything goes all kinds of not good. All right. So what I'm going to do is a bullet, okay, with 2,000 joules of energy. That's what physics says it has. Okay, a tremendous amount of energy. And I'm going to have 10 recoiling guns over on this other side. So we have 10 recoiling guns. And so just imagine I drew 10. And they're only going to have 20 joules of energy. So I certainly am going to have more momentum over here, okay, because we know that the same momentum, the gun recoil has the same momentum, okay, the momentums are equal. All right. I have one atom going 1,000 miles an hour. I have 1,000 atoms going 1 mile an hour. I have the same momentum. But now I've really increased the momentum. I have 20 times the momentum over here. So this is 10x. I'm sorry. 2 and 2. All right, so we have 10x, okay, the mv. You can see that, right? Yeah, okay. 10x the mv on this side. All right, and we have 200 times the Ke over here. So this side has 200x the Ke. This one has 10x the mv. So this one has a lot more momentum. This one has a lot more kinetic energy. And now, instead of the gun recoil going this way, I guess I should have drawn the guns going this way. Okay. The guns are going this way, so now they're going to head into each other. So now we have a collision, okay, and we can do it elastically or inelastically, and it ain't going to matter because we have a real problem. Because frankly, both of these things can't be right. If this is real energy, the bullet has to win. If this is real energy momentum, then the guns are going to win. Now, my simple argument is this is a real contest. This proves which one is real. Whoever wins this battle proves momentum or it proves kinetic energy. And I'd say it decisively will prove momentum. The bullet will not defeat the 10 recoiling guns. The momentum of the 10 recoiling guns will win by 10 times. They have 10 times the energy. They're going to push the collision 10 times in their direction. That's just a fact. The kinetic energy is meaningless. It's meaningless to a spaceship in space. It's meaningless in any circumstance where it actually has to do work. Not where it just makes up a fake number, like they say the space shuttle rockets have 2,468 kilo monsters, megatons worth of energy. They just make up a number for how much fuel there is. So again, I could illustrate this, maybe just a real quickie. I'm sorry, I don't want to really I'm just, asked to be indulged. So if I made a zip gun, okay, so I make 2 zip guns, and so there's an explosive here, same exact explosive in both guns. I put very light bullets in this one, and then I put 1,000 times heavier bullets in this one. I get 4 joules of total energy out of the zip gun here, and I get 4,000 joules of total energy out of the zip gun here. Which one is accurately describing how much energy the explosive had? 4 or 4,000? So again, it just illustrates you can't say this is anything called real physics when you do a test, a perfectly reasonable test to see how much energy the gun, the explosive has, and you get two answers that are 1,000 times out of sync with each other. Can't be reality. All right, now with that context, leave us play the rest of his statement on the subject. Continuing.
Bob and Alice are on the skating rink, Alice having a mass of 50 kilograms. Bob is a little heavier, it's a guy, so 70 kilograms. Alice is skating towards Bob with a velocity VA of 5 meters per second, while Bob is also going towards Alice with a velocity VB of 10 meters per second.
Right. So if he switched those two, right, so we have Alice going 10 and Bob going 5, then Alice would have more kinetic energy and Bob would have more momentum. And that's the paradox. Which one wins?
Obviously,
so in this case, momentum's going to win, but yes, he had more kinetic energy also. So you see, it doesn't really test the theories. But just that simple change, just give Bob the higher momentum, give Alice the higher kinetic energy, have a 10-ton train going 5 miles an hour, having a contest with a 5-ton train going 10 miles an hour, and tell me which one wins. If the collision moves in the direction of the 5-ton train, we know kinetic energy works. If the collision moves in no direction, okay, then we know momentum works.
Crash. But Bob and Alice are very good friends, so they will hold hands. So let me draw this again.
So just holding hands really won't do it, right? Because you'd have to spin or you'd have to do something. I mean, obviously you either have an elastic, which means you're going to allow the two things to just exchange, or you have inelastic where you're going to crush something, break something, cause momentum to leave in some other form. So obviously if it's two blobs of clay, or something like that. But two people aren't going to collide like two blobs of clay. Now you could say they hit each other and his head smashes her in the forehead, gives her a concussion, and she dies. I mean, you could come up with some way where they're combining their energies. But this idea of just saying they hold hands doesn't really say anything. So you're going to say they're going to use up they're going to convert the linear momentum into angular momentum. Fine. And then say there's still going to be some some linear momentum left over. They won't be able to generate enough angular momentum to use up all the momentum, and so they'll spin and move. But see, you're just complicating things by not explaining how they dissipate the extra energy, because it has to go somewhere. The momentum doesn't disappear. It doesn't cancel. You have to drive it into the ground. You have to fly it off as pieces. You have to vibrate the atmosphere. You have to do something with the momentum. It never cancels. There's no unenergy. There's no unmomentum. See, I could get into the whole part where he talks about vectors and scalars, and I've been over that already. Just made up.
That's Alice holding hands with Bob after having crashed into each other. Here, we want to find the final velocity they have after the crash. In what direction are they going, and with what speed?
So there is no crash. But let's just say they're a lump of clay. Let's say Bob is a lump of clay, she's a lump of clay, and what's going to happen is the two lumps of clay are going to deform each other equally. And whatever's left over is going to keep going. So the canceling part will happen by pushing into each other and deforming the clay. And whatever's left over, whoever has the extra energy, the whole thing will move in that direction.
So for this, I will consider the system of Alice and Bob before the crash and after the crash.
So again, they're not really systems. They're individual objects with actual motion. They actually have a force. And you're colliding two forces. And you have to to eliminate any of the force, to get rid of it, you have to use it. It has to go somewhere. So the forces that are going to be canceled will have to be in the form, like I said, of clay deformation, of broken skulls or of broken fingers, or something has to be broken. Something has to be had work done on it. You can't just make the momentum cancel. It never just cancels. There's no collision where momentum is just canceled. You have to crush fenders. So, I mean, you can have cars that have crushable bumpers, and then you can have cars like bumper cars or something where you have springs. And in both cases, you can understand the momentum doesn't cancel. In the one case, it bends a bunch of metal, and in the other case, it completely exchanges and the objects retain the original motion, the original momentum in their motion.
And on this system, I will apply the principle of conservation of momentum, meaning that the momentum of the system before will be equal to the momentum of the system after the crash.
So this is plussing and minusing, which is sort of cheating, because there isn't any plus and minus. He didn't show us where the parts that were subtracted are evident. So he's going to just minus her momentum from his momentum as a vector and say, I'm not going to pay any attention to the parts that, cancel. And whatever's left over, the remainder, whatever's left over after you cancel, he's got the higher momentum. She's got less momentum. You cancel that amount of her momentum, and then you have that bit left over, and that's going to continue. And that's not really what happens in any experiment. Nothing cancels. You have to have friction take it, you have to break something, you have to move something, you have to heat something, you have to use the momentum. The momentum has to do work to leave this system. It was in the system. They didn't cancel. It isn't this minus this. There's no such thing as minus energy. What went in was his complete momentum, what went in was her complete momentum, and in the end you have to show where that went. And if you just show the little bit of momentum of the two bodies leaving at 1/4 of the speed, you won't be showing all the momentum that went in. So it's not really illustrating conservation of momentum, because you pretended essentially that you canceled momentum.
The forces that that Alice and Bob are experiencing are inside the system, so these are not external forces. There are no external forces on the system because there's no...
Yeah, so this whole concept of external forces is just kind of silly. It's always, yes, of course. Nobody's saying all of a sudden a talking chicken showed up. I mean, there's no, we're showing the elements. So even if there's gravity, even whatever's in there, it's not an external force if we're already calculating it. We're already giving it a place in the experiment. So, but it's this idea of looking at this as a system is, in my opinion, just wrong, because it's just energy. And you're just figuring out where does the energy go. And the fact is, like Richard Feynman would say, you have to account for all the blocks. You start with a certain number of blocks moving. You have to have the same number of blocks moving in the end. And he basically just took a whole bunch of the blocks and just said they canceled, when they can't just cancel.
Friction. So we can apply conservation of momentum. Why don't you try? Pause the video, give yourself a few minutes, and try to find out what will be the final velocity v.
I really hate these parts of video. So this is just a personal statement I would make as somebody who has learned on his own. Okay, this this effort to force me to do math rather than do understanding is really just annoying, frankly. This little math test they put in the middle of their lectures. That's not high entertainment for me personally.
As you can see, for clarity, I replaced Alice and Bob by balls. I want to calculate the initial momentum of the system formed by these two balls.
Right, and then what you should do side by side is calculate the kinetic energy. And if you just change this one factor, made her speed the 10 meters per second, make his speed the 5 meters per second, then you will be illustrating what I would claim would be a real problem, where you're going to have to explain where the kinetic energy went, why the kinetic energy didn't win, why momentum won and kinetic energy decisively lost.
So the momentum of the system will be the sum of the momenta of the constituents of the system. But these are vectors. It's a vector addition, so I need to define an axis.
And it's always addition. There's no such thing as a true negative vector. There's always positive motion relative to what Newton would say. I mean, Newton would say this, and again, nobody talks about it, but Newton would say space is a place. It's not moving. So I could just take a hunk of space somewhere, and the hunk of space is not moving. And everything else is moving relative to that not moving thing. And everything else that is moving has force. It has momentum. And the forces can't cancel. They have to do work against something. So they have to do this. Back and forth thing. Or, that's the elastic version. Or they have to do the inelastic version where they convert it to heat going that way. Or some other photons going this way. Or some other energy leaves in some discrete form. But it's real motion still in the universe. Little atoms moving. You can never have an anti-motion in the universe. There's no anti-motions. It's all positive motion. Any motion is a positive motion.
Positive axis, but let's consider it positive this way. Now, I can calculate the magnitudes. By removing the arrows, I realize the momentum of A is this way, it's positive. And that of P is this way, it's negative. And I can replace P by mv now. Let's calculate now the final momentum of the system. So it will be Pf. The system now is made of the two balls which are clung to each other. They form one single object of mass ma plus mb.
Right, but to do that smashing together, if they don't bounce against each other or they don't do something else, then you still have to get rid of that extra momentum. It doesn't cancel. It has to be clay, and you have to move a bunch of clay and heat the clay. You have to use the momentum. You can't just cancel the momentum.
And because they are the same object, they go at the same velocity. Now here I can easily remove the arrow here because it's not an addition. V is just collinear with P. So they have the same sign. And this is now that the magic of conservation of momentum is going to show up. This equal to that because this is equal to that. So let's write this. MAV.
So he's just saying the difference that went in is the difference coming out. But the point is that what really has to be the same is the total motion going in has to be the total motion coming out. And there he did not conserve because he did not show us how much Alice and Bob hurt each other. Because they have to. If they don't keep the motion as linear motion, then it has to disappear in some other form of motion.
A minus MB.
If it's not inelastic, if it's not elastic, these words, I have to keep thinking which one is which. Oh, it's just so irritating. If they're not going to bounce, then they have to crush.
E equals MA plus MB V. If I rearrange this, I can write down, I'm going to plug in numbers. MAVA minus MBVB over MA plus MB equals V. So that was 50 by 5 minus 70 by 10 divided by 50 plus 70. Let me calculate this.
So this is just the remaining momentum
I
after.
find minus 3.75 meters per second.
And that's because he said, which doesn't make much sense, frankly, that Bob had the positive direction. Well, Bob had the higher momentum, so Bob's direction is going to win. So somewhere the signs got messed up here. Because, frankly, she's not going to win. He wins. Okay. So there's still something wrong there, I think. I didn't do the total momentums. Okay, so 10 times 50 is 100. 5 times 70 is still, yeah, Bob was the winner, so it should have come out positive, frankly. I don't know exactly how he made it turn out the other way. But it doesn't really matter. I'm not going to argue those little minutia details. Doesn't matter. The point is that it's really not accurate. Because what went in was both motions, and what has to come out is that total amount of motion. And frankly, that's the simple argument. If it was an elastic collision, if they banged into each other and had to keep the motion as movement in the two main bodies, then that number would be a lot higher. Okay. All right, anyway, so I think that's probably enough. I mean, we don't need to beat a dead horse. So the idea is I'm going to hope this guy will give me the opportunity to do this. He does these tutoring things on Skype, that he'll allow this, where I can interrogate him essentially on his physics, what he believes and why he believes it. I can talk a little bit about the history. I'll give him all the questions in advance. I'm not trying to embarrass him, but the truth is that the physics needs to be defended. I'm arguing that you are slandering Newton. Okay, you scientists talk about Newton, you talk about his laws, but you don't pay any attention to his physics. And the guy Newton hated more than anybody on earth, Leibniz, is the guy whose physics you're really selling. You're Leibnizians. Okay, you're not Newtonian, and you ought to be honest about that you don't like Newton's physics, that you reject it, that you don't think Newton understood motion in the universe. You ought to be able to say make these direct accusations, that he formulated his laws and only accidentally got right answers because he didn't understand what energy was in the universe. And the same for Descartes, to point out a Frenchman. You're really just thumbing your nose at everything Descartes ever did or ever said. And the same for Galileo. You're just ignoring what he revealed, and what he revealed is the huge fact that gravity is a time-dependent force. It's about how long you're falling in it. It's not about how far you're falling in it. It's about how long you're falling in it. All right. So those are probably enough of it's plenty to chew there, I think, and we'll see if we get any kind of reasoned response. But this is what I'd like to do for the 2 hours, if we can agree on terms. I really don't think I should have to pay a physicist to defend physics, but whatever, I'm willing to. I'd just like to get answers to how these paradoxes are for you acceptable. That the fact is your kinetic energy theory will lose if we have the tug of war, okay, between the guns and the bullet. Your side loses. Your theory loses. It loses in space, it loses on the ground, it loses no matter where we do the contest. And it's just a fact. The kinetic energy theory is a fable, and it doesn't have anything to do with accurately understanding the physical universe. That's my assertion. So we'll play his conclusion since it's next anyway.
So the magnitude of the velocity they have after the crash is 3.75 meters per second, and the direction is that way.
And the total momentum is missing. So we're missing a big giant hunk of the total momentum because it got used up doing however they crashed. Whatever their crash was, the total momentum is, the blood on the ice, that we didn't get to see.
The notion of momentum is quite straightforward. It characterizes the amount of motion, the quantity of motion of a body or of a system of bodies.
So he says that in one of the videos, that he likes quantity of motion as a phrase. I mean, that was the Descartesian phrase. Newton used the same phrase to describe energy. And frankly, they were describing energy. the words were synonymous for them in the sense they didn't have the word energy, but if it existed, Isaac Newton would be saying momentum is energy, clearly.
And it is subject to a conservation law. And this conservation law is a cornerstone of physics.
So this is the part that doesn't make any sense because, look, I could show you lots of examples where there is no conservation, where I crash a light thing going fast into a heavy thing and I end up with more momentum, free momentum. So, and certainly it's by Newton's definition of the conservation law, equal and opposite reaction, kinetic energy has no respect for that at all.
Conservation of momentum allows to calculate and deduce information that otherwise can be difficult to measure. For example, conservation of momentum is at the heart of experimental particle physics.
Unfortunately, it's not true again in the sense that they're not conserving momentum, they're conserving kinetic energy. And that's why they think things are, they think a single proton flying into the atmosphere, could knock over the Empire State Building because they've given it an insane amount of power and energy because it has a high velocity. The v squared just turns little light things into these entities that can do all of this work. And again, it can be proven that they can't do it with my bullet analogy. Okay, 1 bullet against 10 gun recoils, the bullet decisively loses.
Yes, some particles are not directly detectable. We cannot see them. They decay too quickly.
So, all right, so this whole decaying thing is, again, just sort of bullshit. It's not particles don't decay. Arrangements of particles fall apart. Okay, atoms decay. Particles don't decay.
By analyzing the momentum of the decay products, we can deduce, using conservation of momentum, we can deduce information about this short-lived.
Right, now I'm arguing that the deductions are all wrong, okay? So the fact is you're telling me my electrons and protons, the mass of my electrons and protons do not add up to my weight, okay? That I can't, it's only 1% of my weight can be accounted for in the mass of electrons and protons. My argument to you is the only reason why you think that or say that is because you use the kinetic energy formula to decide how heavy an electron is and how heavy a proton is. And if you used momentum to decide how heavy they were, you would be saying that you weigh what your electrons and protons weigh. They are your mass. Your atomic weight is your weight.
Particle. But that topic will be for another video. Thank you for watching. I hope you found this episode useful to you, and I also hope that now you are a master at manipulating momentum.
Yeah, so again, the whole objective is the truth, and what I'm saying clearly is I don't think this is entirely honest. I don't think it's fair to... You're not standing on the shoulders of giants. You're sort of pooing on them. You're stomping on them. That it's so unfair to what all the work that was done in all the years, to acquire the hope of being able to see the future, to see better. I mean, all the mountain climbing to get to this better point of view, and I would argue in the last 200 years you threw it all away on wooey mush, so just weird speculation. Find the least likely to be true answer and cherish it and throw away the simple answers. All right, that kind of thing. I mean, look, I'm simply making the accusation what you're teaching isn't accurate, and it doesn't get right answers, and it doesn't do any of the stuff you say it does. It's not right. It's not the truth. It's not accurate. All right. So that's enough of a video. We'll see what happens. Again, it's no personal offense, but is there any other, we're disagreeing. Catholic, Muslim. I mean, I'm saying you're wrong, okay? I'm saying your theory is wrong, and I don't know how to say that without saying you're wrong, okay? Yeah, nobody wants to hear that. But the point is you have to make arguments, and you have to have evidence for arguments. So until you show me it taking 25 times the fuel to spin a motor 5 times as fast, I'm going to remain entirely unconvinced that you know what you're talking about, that you have any good reason to believe it does. Do you have any good reason to believe it takes 25 times the fuel to spin a motor 5 times faster? Do you have any good reason to believe that? Any physical good reason? Any evidenced good reason? All right, enough of video. So till the next time and such.